Okay, this is about regular polyhedra with regular polygons as faces. There are exactly five regular polyhedra, no more, no less, that could be constructed with each face being a regular polygon. There's the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. The tetrahedron is kind of like a pyramid. It has 4 faces. Cube has 6. Octahedron has 8. Dodecahedron, as the name says, has 12. And icosahedron has 20. Okay, so the tetrahedron has, with the 4 faces, has 4 vertices and 6 edges in the figure. Cube has 6 faces, 8 vertices, and 12 edges. The octahedron has 8 faces, 6 vertices, and 12 edges. The dodecahedron has 12 faces, 20 edges. 20 vertices and 30 edges. The icosahedron has 20 faces, 12 vertices, 30 edges. Now we can group these 5 so-called Platonic solids into 3 categories, which we call duals. We call them duals because when one figure is inscribed within its dual, the vertices of that figure touch each of the faces of the other figure. Okay, for example, we have the tetrahedron. That's actually its own dual. If one inscribes a tetrahedron within a tetrahedron, the vertices of the inscribed tetrahedron touch the faces of the outer tetrahedron. And for the cube, right, we can inscribe the octahedron in the cube, or the cube and octahedron, same story. And likewise with the dodecahedron and icosahedron pair. Now, it's no coincidence that in doing that, we have 3 categories of numbers of edges. The tetrahedron has 6 edges. Cube and octahedron both have 12 edges. And the dodecahedron and icosahedron, they both have 30 edges. So what happens, right, when we're for the duals, the numbers for faces and vertices switch. So when you switch 6, 8 for the cube, you get the 8, 6 for the octahedron, and 12, 20 dodecahedron becomes 20, 12 for icosahedron. Okay, so I've also noticed, right, that the regular polygons that form the faces, there's the same polygon, same regular polygon that forms all the faces for each of these polyhedra. I've noticed that, right, the cube all its faces are squares. The dodecahedron, all its faces are regular pentagons. And the rest of them, the tetrahedron, the octahedron, and the icosahedron, their faces are all equilateral triangles. So notice, right, there are only 3 types of regular polygons that form the faces of these polyhedra. There are 3, 4, and 5-sided polygons: the triangle, the square, and the pentagon. Okay, all these numbers, if we take these numbers of faces, vertices, edges, and put them into what we call the Euler formula, F for faces, V for vertices, E for edges, the numbers work. The numbers of faces plus the numbers of vertices for each of these polyhedra equals the number of edges plus 2. Now for the full Euler formula, we also have minus T. The T stands for topological value. Topological value, yeah. T. But for all these polyhedra, all these figures, that value is 0, so we ignore this. And for our purposes, F plus V equals E plus 2 is the formula, Euler formula. Okay.